Welcome to Mutlu Learning Hub. Today we'll talk about a situation almost everyone runs into in machine learning. Your model has very low training error, and yet when you try it on new data, performance drops sharply. In this video, we'll unpack why this happens and how to recognize it early before you waste time tuning the wrong model. The real goal of machine learning is generalization, not performing well on the data you already saw, but performing well on new unseen data. A model can always drive training error down if it's flexible enough. That alone does not prove it learned anything meaningful. That's why we split data. Training answers, did I fit the data? Testing answers, will this work again? Here is what we'll cover. First, why near zero training error can be misleading. Then, how to visually recognize underfitting and overfitting. After that, what to check when a model fails in practice. And finally, some simple rules you can use to fix models without guessing or blindly tuning hyperparameters. In practice, we split data in two steps. First, we hold out a test set and don't touch it. This is our final reality check. Then we split the remaining data into training and validation. Training is where we fit the parameters. Validation is where we make the decisions, how complex the model should be, and when to stop learning. The test set is used once at the end to evaluate true generalization performance. We'll start with underfitting. Here, the data follows a curved pattern. And let's see what happens if we try linear regression. As you see here, the model is too simple to capture the curved pattern. No matter how long we train, the model just can't bend enough to follow the structure in the data. Underfitting happens when the model has low complexity. It misses important structure in the data, and because of that, both the training error and the validation error stay high. The model is too rigid, like trying to summarize a curved story with a straight line. Underfitting usually happens for three reasons. The model is too simple, important nonlinear relationships are ignored, or the features don't contain enough signal. To fix underfitting, you generally need more expressive power, a more flexible model, better features, or less excessive regularization. Importantly, just adding more data won't fix underfitting if the model can't represent the pattern in the first place. Now let's look at the opposite problem, overfitting. This model is extremely flexible. It passes very close to every training point. The training error is very low, but the curve is clearly following noise, not signal. Overfitting happens when the model is too complex for the amount of data we have. It learns random fluctuations instead of the real pattern. That's why overfitting shows up low training error but high validation error. The model looks impressive on training data and then fails everywhere else. Overfitting usually happens because the model is too flexible, the data is limited, or the training set is too specific. To fix it, we limit complexity, we use regularization or early stopping, we collect diverse data when possible, and we use cross-validation. Note that near zero training error is often a warning. When a model fails, the first step is diagnosis. If training and validation errors are both high, that usually means underfitting. If training error is very low but validation error jumps, that's a classic sign of overfitting. If results change a lot across data splits, don't trust a single score. Always start simple, increase complexity carefully. Make decisions based on validation, not training, and look for stable performance, not perfect scores. Thanks for watching. In the next video, we'll connect this intuition to bias, variance, and trade-offs between them.